also do a lot of integrated optics, nanophotonics characterization, which is what we do in this lab, and which is the area I work in. So I'll be talking a little bit about that. So we work with stuff like photonic crystals, integrated waveguides, ring resonators. We put them together to do optical add-drop filters, and all that stuff. So I'll be talking about maybe some recent work within the photonic crystals. And I don't know how familiar you guys are with photonic crystals. If you know what photonic crystals are, have an idea. But a brief introduction is, if you take a dielectric mirror, basically a stack of high index, low index, high index, low index, that's actually considered a 1D photonic crystal. If you extend this out to 2 or 3 dimensions, then you have the structure which is actually the structure known as photonic crystal. And this photonic crystal, they can allow for a lot of interesting phenomena. And one of them is this self-guiding effect, or supercollimation effect, or self-collimation effect, and it's a totally linear effect. So, and the way it works is, well, if you all know, if you just launch a beam in an isotropic medium, it will just diffract naturally, right? And the smaller the beam, the more diffraction angle is. So, in this case, but in this kind of materials, you can eventually have propagation without diffraction, which is something that is not very clear, right? So, if we just look at diffraction, from a mathematical point of view, we can think about, say, you launch a small beam, in this case a 2-micron beam, into your material. And now think about this beam as being, just take the Fourier transform in space, and think about it as being composed of several beams of specific frequencies, like just take the Fourier transform. So now if you think, let each one of these frequencies propagate through space. And each one of them will have a different propagation constant. And the relation exists with the well-known we have in the background. It's just a circle. So this circle determines what the propagation constant will be for each one of the spatial frequencies that you propagate. And so when they propagate, they all have different propagation constants. And this just translates, if you take the inverse Fourier transform, you just get in real space a beam that spreads as it propagates. So now if you can have a material, or if you can build a material that would have flat dispersion surface, that would have the same propagation constant for each one of these individual components of the beam, then when they propagate, they will all acquire the same phase shift, and this will translate into actually a collimated beam, a beam propagating without diffraction. And this is actually, so there's no physical boundaries here in this horizontal dimension. So it's not a waveguide, you cannot call it a waveguide, but you can still have like some propagation, some guiding, because the propagation is actually without diffraction. So the way we do this is we build one of these 2D photonic crystals, and this is just an SCM of it. And this one specifically was built in Leslie Kolodziejski's group. I believe you guys also visited that lab earlier. And it's basically a thin layer, 200 nanometer layer of silicon with a bunch of air holes, a square lattice of air holes. And this specific crystal will have a dispersion relation, which is shown here, with some flat regions for specific wavelength. So in principle, if we propagate in the right direction of light at this specific wavelength, we should have propagation without diffraction. And this is what we actually first simulate up here, and then we show down here. So basically, we take this thin layer of photonic crystal, and we launch light into it. And as we change the wavelength, we see that for a specific wavelength, there is no diffraction. And at this frequency, or this wavelength, we are operating exactly over this flat surface. And this is about 500 microns, and it's a 2-micron beam inside. So put a small 2-micron beam inside, and it's propagating 500 microns without diffracting. And we also identified, well, this is over 500 microns, but we want to see how far we can go with this. So we actually took a 3mm sample, and we put light into this 3mm sample. And again, we propagate it, and this is just a top image with an IR camera, and it seems that you have a collimated beam inside. But to precisely see the beam size and to characterize this beam, we do near-field scanning optical microscopy. So basically, we detect the evanescent field. As you guys know, in the fiber, the light is guiding the core, but there's some evanescent field declining. Here it's the same, so the light is guided inside this structure, but there's some evanescent field extending into the air. And if we detect that field, then we can actually see the profile of the beam inside. So that's what we do here. And this is at the input of the 3mm sample, 1 millimeter, and at the end of the 3 millimeters. So, and we see that we have a consistent 2 micron beam propagating inside this photonic crystal. And we did something similar with the 5 millimeter sample. And now instead of taking these top images, we actually just looked at the light at the end of the photonic crystal, basically at the end of the 5 millimeters. And this is the mode that we have. It's also 2 micron beam. So we don't have the results here, but we did similar, the same experiment with an 8 millimeter sample. So basically approaching a centimeter, and we're propagating a 2 micron beam without diffraction in this kind of material. So that's something very interesting and actually important. So
would you say it's 2 micron? Or
yeah.
How long is it staying 2 micron?
Well, we showed over 8 millimeters. But of course, I mean, one of the small problems here is the structure is not optimized for loss. So if you're seeing light from the top, it means that you have light scattered out of this system, right? So the loss is actually huge compared to 3.6 dB per millimeter. But if you think about this, if you want to use this for optical interconnects on chip, on much smaller scale, then this could be a solution. And because basically you can guide light without having physical. Well, except for this, of course, thin wave. So, and we got a good publication, so on the cover of Nature Materials. So this is some really cool stuff right now. In addition to these kind of structures, as I said, we have this integrated waveguides, ring resonators. We're also working now. I believe you guys also saw Hank Smith's group lab. Yeah. So they're also doing some really cool optical ladder filters, tunable actually. So like tune these filters, and this is all in doing. Other than that, we do on-chip couplers, polymer waveguides, all sort of other stuff. Any questions?
Who financed it?
A lot of people. So this specific work was done by in this Interconnect Focus Center, or Marco. It's digitally the semiconductor industry. So we got some money for this specific project. Other than that, we have the DoD, the Air Force. We have several sponsors. Any other questions? So basically, what you see around here are the setups that we build to actually be able to characterize and get all these nice results. And if you're curious to see how these devices look, physically, I'm just going to pass along this. So you don't see the devices themselves, but you see those small parts of the wafer with the devices in there. So that's actually what we take and we measure.
Instead of having a holy fiber, uses only photonic crystal.
Yeah, this is the photonic crystal fibers are the concept is similar, but this is just a planar thing. Yeah.
When you mentioned the loss, is it primarily due to things like Fresnel reflections on the galactic interfaces, which are so many there? Or?
Yeah. So basically that's it. So the losses, we believe that they are mainly due to the reflection in each one of these small interfaces, and because they're not perfect, they're rough, and that's why you see that's a loss mechanism.
Would you see some interference patterns inside there because you take a coherent beam and now you have multiple surfaces of reflection? Or?
Well, we didn't see that inside, but you could see. Because you have all this interfering, but we didn't look into that. Any other questions?
I have a question.
Sorry, to get this one? Oh, this basically we build a system. We just